Today we will learn about numerical solution of partial differential equation. In numerical solution of PDE, partial differential equation, in the first subtopic, we will learn about the classification of second order PDE, which is the parabolic, hyperbolic and elliptic. And then we will go through the second subtopic, which is the finite difference method, FDM. In this subtopic, we will only cover FDM for parabolic problem. The first subtopic is the classification of second order PDE. The partial differential equation or PDE is an equation that contains two or more independent variables. In the previous chapter, the ODE only have one independent variable, but in PDE you can have two or more independent variable. So many applications to PDE such as in dynamics, elasticity, heat transfer, electromagnetic theory, quantum mechanics and others. Okay, so what is the meaning of second order PDE? What is the meaning of order? Order of the PDE is the order of the highest derivative involved. So let's say you have this example, order of PDE del u del x minus 2u equal to x squared. So you can see here the highest order of derivative in this case is equal to 1. So this is first order PDE. And then del u del t plus del squared u del x squared equal to exponent to x. In this case, the highest order of derivative is equal to 2. So this is the second order PDE. PDEs of the second order play an important role in describing many physical phenomena in mathematical physics and engineering. The most general form of linear second order PDEs in two independent variables x and y can be expressed as, this is the general form of the second order PDE. A del squared u del x squared, b del squared u del x del y, plus c del squared u del y squared and the rest. The order must be like this. Start from A times 2 uxx, b times 2 uxy, c times 2 uyy and so on, where A, B, C, D, E, F and G are the constant coefficient and u is a function of the two independent variables x and y. The linear PDE can be classified into three categories such as parabolic, hyperbolic and elliptic. From the general form of second order PDE, the most important part is A, B and C, these three. Okay, because we will use this to classify the categories of the PDE. Okay, there are three types of PDE: parabolic, hyperbolic and elliptic. Why must we classify the equation? It is because for different types of PDE, we have different types of solution or different type of method to solve the equation. To classify, we will use this formula. This is how we use the value of coefficient A, B and C. So you know that A is the coefficient of uxx, B is the coefficient of uxy and C is the coefficient of uyy. So you have to determine what is the value of each of these coefficient A, B and C, and then substitute into this equation. Check whether it is equal to 0, greater than 0 or less than 0. If it is equal to 0, then the PDE is the parabolic. If it is greater than 0, for example, the value is 4, then it is a hyperbolic equation. If it is less than 0, for example, -1, then it is a elliptic equation. Other than parabolic, hyperbolic, and elliptic, it also can be an equation of mixed type. Okay, let's look at example 1. Classify each of the following constant coefficient equation as hyperbolic, parabolic, or elliptic. So this is the general form of second order PDEs. Okay, this is UXX. A is the constant coefficient of UXX. In this case, A is equal to 1, B is equal to 2, and C is equal to 3. So with all this value A, B, and C, substitute into this equation. B squared minus 4AC. B squared, 2 squared minus 4. A equal to 1 and C equal to 3. Simplify. Then you'll get -8. -8 is less than 0. So it is an elliptic. For number 2, let's determine the value of A, B, and C. Okay, A is the coefficient of UXX. Okay, so A is equal to 2, B is equal to -4, and C is equal to 2. Again, substitute into this equation. Simplify, then you get 0. So this type of PDE is the parabolic equation. Number 3, A is equal to 1, B is equal to 5, and C is equal to 4. Okay, substitute into this equation. Simplify it, then you get 9. 9 is greater than 0, so it is hyperbolic. Okay, so that's how you classify each of these PDEs. Similarly, for example number 2, classify each of the following as hyperbolic, parabolic, or elliptic at every point xy of the domain omega. In this case, question A, your A is equal to x squared. This is your A. B is equal to -2xy. And C is equal to y squared. Substitute into this equation. B squared minus 4AC. Simplify this, then you get 0. So this is parabolic. Question number 2. A is equal to exponent x. B equal to 0. B is the coefficient of UXY. So no UXY here. So B is equal to 0. C is equal to exponent y. So substitute into this equation. Simplify. Then you get -4 exponent x plus y. So -4 exponent x plus y is less than 0. So it is elliptic. And question number 3. A is equal to 1. B is equal to 1. And C is equal to -x. Substitute into this equation. Simplify, then you get 1 plus 4x. So this is the mixed equation. Mixed equation means if x is less than -1.4, it will be elliptic. Okay, why? Because if you substitute this value into this, you will get b squared minus 4ac less than 0. So it will be elliptic. And if you substitute x is equal to -1.4, here you will get equal to 0. So it is parabolic. And if the value of x is from -1.4 to 0, you will get the value of this greater than 0. So it will be hyperbolic. The second part of this chapter is the finite difference method for FDM. So this method is one of the simplest and oldest method to solve the differential equation approximately. The basic step for FDM: first, divide the solution into grid of nodes or discretizing the domain, and then approximate the differential equation and boundary and initial condition by a set of linear algebraic equation or finite difference approximation within the solution region, and then solve the equation. Discrete grid points. Okay, we start with the starting point where the position of this point is ij. Okay, this point, this is ij. Next point will be I plus 1j. So in this case, j remain. J only change if we move up or down. And then at this point, I minus 1j. At this point, I is remain because I is the value of x. So j change to j plus 1. Here, I remain, j become j minus 1. Here, I plus 1, j becomes j minus 1. At this point, I minus 1, j minus 1. And here, I minus 1, j plus 1. And here, I plus 1, j plus 1. So let's connect this. Okay, so this value here is the difference of x or h. This value here, difference of x or equal to h, the step size. And then here will be the difference of t, or also known as k. So this figure shows a discrete point with difference of x and difference of t is spacing in x and t direction respectively, here and here. So in this chapter, we only cover the finite difference method for parabolic problem. So this is the general form of the second order linear PDE with two independent variables, x and y, and one dependent variable, which is u. Recall the criteria for an equation of this type to be considered parabolic. Okay, classified as parabolic, it must satisfy b squared minus 4ac equal to 0. Example 3. Solve the following initial boundary value problem for the heat equation using finite difference method up to t equal to 0.02. Take difference t equal to 0.01 and difference x equal to 0.2. Okay, this is your h and this is your k. You can write this in the simpler form. Ut is equal to u xx. So u xt means the temperature at position x and time t. So this is your boundary condition. And this is your initial condition or initial temperature. Okay, let's solve this. Step number 1, write the heat equation in the form of finite difference approximation. Then, by algebraic manipulation, find ui t plus 1. You need to find ui t plus 1. So just rearrange this equation. Okay, you get this equation. You derive this from forward difference formula. Okay, solve for ui t plus 1. Okay, letting this k over h squared as r. You'll get 0.25. Then you can write this equation ui t plus 1 is equal to 0.25 ui minus 1t plus 0.5 uit plus 0.25 ui plus 1 t. And then step number 2, form a grid cell. Then determine the endpoints, which is this yellow points, and interior points, the green points here, from the condition equation. Okay, this is the given condition. This is your x, and this is value of t. So you know that k, or the difference of t, is 0.01, and h, or difference of x, is equal to 0.2. X is from 0 to 1. So here your x will be x equal to 0, and then x equal to 0.2, x equal to 0.4, x equal to 0.6, x equal to 0.8, and x equal to 1. The difference between two grid points is equal to 0.2. So you just add up 0.2 until you get this x equal to 1. And then the boundary condition u0t is equal to uit is equal to 0. So here your t is equal or greater than 0. So here your t will be t equal to 0, t equal to 0.01, t equal to 0.02. So the boundary condition here, all these values here must be equal to 0. Okay, from this condition. So let's label these nodes. This is U00, U10, U20, U30, U40, U50. And this is U01, U02, U51, U52. So this is equal to 0, equal to 0, equal to 0, equal to 0, 0, and 0. So now you just get all the values of the yellow point. So all 0 for the yellow points, and for green point you have to substitute this value of x into this equation, this x into this equation, and also this x into this equation. Okay, so that is the step number 2, find the yellow and green points. Step number 3, determine the remainders of the interior point, red. Okay, so let's draw the red points. We will have this 1, 2, 3, 4, 5, 6, 7, 8. The value of each of red point can be obtained by using the values of 3 points below it. For example, this value, this is the value of U11. So you can use the value of 3 points below it, which is this point, and this point. Similarly, for point U21, you can use this point, 3 values below it. Okay, in details, the grid can be written like this. So this is the boundary condition, all zeros, value here, the yellow point, And this is how you get the value of the green point. Okay, the first green point, U10, second green point, U20, the third green point, U30, and the fourth green point, U40. This equation is given in the question. So at this point, x is equal to 0.2. Just substitute 0.2 into this equation. So at this point, U10, 0.2 times 1 minus 0.2, then you will get 0.16. So the value here will be 0.16, here 0.24, 0.24, and 0.16. Okay, so now let's find the value of these red notes. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, we just use the formula that we manipulate in the step 1. Okay, this value. Okay, so we will use this value for each of the red points. For note 1, okay, note 1 here, this is U11. So U11 will use this value, and this value. So 0.25 UI minus 1t will be U00, UIT will be U10, and UI plus 1t will be U20. So you know that U00 is equal to 0, U10 equal to 0.16, and U20 will be 0.24. Okay, just substitute all this value of U's into this equation, simplify, and then you will get 0.14. So this value, the value of temperature here is equal to 0.14. So you will use the same calculation for each of these notes, the red point. So this will be your answer. Okay, the first note, second note, okay, point number 3, point number 4, point number 5, 6, 7, 8. So now let's look at exercise 3.8. Use the finite difference method to calculate the temperature distribution of the following initial boundary value problem for the heat equation. Only for T, 0.001. Take different T, or K is equal to 0.001 and H is equal to 0.1. So this is the value of X and T. This is the boundary condition and this is the initial condition. Okay, this is your answer. U11 is equal to U91. You get 0.176. U21 is equal to U81, 0.316. U31 equal to U71, 0.416, and the rest. So first, you have to draw the grid point. So we start with this. Look at this. X is from 0 to 1, with H is equal to 0.1. So point here, X equal to 0, X equal to 0.1, X equal to 0.2, X equal to 0.3, 0.4. Okay, and only for T 0.001. So T equal to 0 and then T 0.001. Okay, so now let's connect this. Then the boundary condition, the yellow point here is equal to 0, and then the green point, the initial condition, initial value, initial temperature, and you have to find the value of the red point. Okay, let's label these nodes. So this will be U00, U10, U20, U30, U40, 50, U60, U70, U10, then here U01, U11, U21, U31, U41, U51, U62, U61, U71, U81, U91, and U101. Okay, so we just finish sketch the grid points. From this condition, you know that the boundary values are 0. This will be equal to 0, equal to 0, equal to 0, and equal to 0. So you need to find the green point. So this is the yellow, and this is the green point. This is the red point. This is the value of U10, U20. Okay, these are the value of the green point. To find the red points, okay, similarly, you need to substitute the value of, you can use the value of these 3 points below it. 1, 2, 3. Okay, so you know this value, and this value. Just substitute into the equation that you rearrange. Ui t plus 1, the general formula. Ui t plus 1. Okay, substitute for each node. 1, 2, 3. So let's label it. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I just calculate for node 1, node 2, and node 3. This is the answer. So you can check your answer. You need to calculate until node 9. Okay, check whether you get this answer or not. So that's all for today.